Welcome to the optical communication course. Today we start here a coherent detection. So in optical communication system, so generally there are two types of detection. You can say that a heterodetection, we can say that a homodetection. And these are the two detection techniques that are used in your optical system. That's why it is called as a coherent optical communication system. Here, the detection of a signal means what? We have a photodetector. When the light falls on this photodetector, that photodetectors convert that optical level or a photon in terms of a electric field. Or we can say that in a electrical level. So means what we can say that a optical signal will convert it into a electrical signal here. So that's why we can say that the modulation technique used in optical communication, that is a intensity modulation with a direct detection. So means we say that a light propagating from the propagating through the link. So now what will be the basic input format of your light waves, and then that light wave is propagating through the system, and then how that light waves are detected through the system. That's why we need to learn about a coherent detection and how that a light wave system is there. So we need to learn first what are the various techniques that are used in the coherent light system. So now we say that we have a light emitting diode, or we can say that a laser. That is about a source. And from that particular source, we are supposed to say that we have this light emitting from this, and then we can use either before, uh, we can say that a modulator, we can say that a modulator is there. Generally, you can say that modulator and then source. Okay, so just consider it. We have the modulator and the source. These are the block of a transmitter, and then a light comes out from this transmitter block that is supposed to be propagating through the optical fiber. This we can say that optical fiber. And then we have a detector at the end. Then light falls on the detector, and then we can say that that output of the detector that is to be given to the amplifier, and then we have the filter and a demodulator. And after that data, we will receive them. Generally, that length of the fiber is too large, so that's why we supposed to be say that this way that length of the fiber is large. And here we have the a factor or this particular component at this particular site. We can say that receiver. And here we need to use a optical coupler. Again, here we need to use the optical coupler at the transmitting side. We need to use the optical coupler at the receiving side, and then we're supposed to transmit the data here. Now is a signal, whatever we have a data input to the source, Then that data is converted into a light form or optical form here, and then that data is transmitted through the optical fiber. And then at the detector, we have the detector component. Now here we need to see that receiver, how it works. So that's why you can say that this receiver is nothing but what we can say that a coherent receiver here. Generally, if you see that there are the various modulation technique used in the optical communication system. So if you see that modulation technique, that is a amplitude shift keying, then we have frequency shift keying, then a phase shift. This amplitude shift keying, or we can say that on off keying. Okay, on off keying. So in this particular case, if you consider that optical shift, amplitude shift keying or on off keying, in that case, that phase of that wave is constant, only that signal amplitude will varying according to that whatever the bit we have. So means we can say that whether we transmit the bit 1 or whether we transmit the bit 0. So according to that, your amplitude will vary. Okay, so means suppose for example we say that there is 1 bit amplitude is increased, for 0 bit amplitude is decreased. Okay, so that is about a amplitude shift. In the case of a frequency shift keying, here we can say that a phase is a constant and your amplitude variable. Now in the case of a phase shift keying, if you see that your amplitude constant and here we can say that there is a variation in the frequency in this frequency shift keying. Okay. Now in the case of a PSK, we have this varying only the phase here. Okay. So means we can say that here we have the variation in the frequency from F1 to F2, or that F1 represents bit 1 and F2 represents bit 2, like sorry bit 0. Likewise, similarly we can consider that here in the phase shift keying, the phase of this particular signal is varying. That is called as a phase shift. So now the detection technique here. So we can say that that particular electrical signal, that data in, that will be modulated here, and then we'll get that optical signal here, and that optical signal is transmitted. That optical signal is transmitted through the optical fiber, and then that will be detected at the detector, or whatever the optical signal comes from this through this getting through this particular fiber from this transmitter, that will be detected at the receiver there. And then here we have a demodulation takes place, and then we'll get that a data. So generally what here, so detection of a data, which can say that from this optical signal to the electrical signal, the detector output is in the form of a current here. So what will be the output in the form of a current, that is the detector current, that we need to be see here. So that is about, we can say that a detection technique of your system there. So to understand this phenomena of transmitter and receiver, so we should understand that what input signal we are transmitting. Suppose I am saying that that signal is transmitting, that is about a cause of omega st plus pi s of t. This one we can say that is signal frequencies, or we can say that the optical signal frequency or optical signal carrier frequency there. And this pi here, we can say that for that optical signal, a phase. And this AS is nothing but the amplitude of the optical signal. So now if we consider that ASK, FSK and PSK, so one of the factor is varying here. And according to that, modulation will be takes place. And then at the receiver, we are detecting the signal and then we'll receive the signal there. Now in generalized case, if you consider that for a transmitter, so what happen generally, we have a signal input, then we need a mixer here, and then we transmit the signal at a higher level. So before that, we need to modulate that signal, and then likewise. Okay, so either we can use a up conversion or we can use a modulator and convert the signal at a higher level, and then we get the signal out here. Similarly, at the detector, we need to use a demodulator or we need to use again a mixer to convert that whatever the output we have. We use a local oscillator for the conversion or for the modulation. Now then we say that here omega s is nothing but a optical signal carrier frequency. Similarly, at the receiver we need to detect that the signal, so that's why we need to use a local oscillator, so that will detect that whatever the signal transmitting through it. That is just like a detection technique. Now then we talk about that it two types of a coherent detection we say. So in that case we say that heterodetection and a homo detection. So at the receiver, that optical power received at this particular place, it is depending upon that what light is propagating through the fiber. So means we say that the current is there, or we can find out that in terms of a power, and that power is depending upon that a light here. So that's why earlier what we say that it is nothing but a light intensity modulation, because light is propagating through it, and we are just modulating the signal. That's why you can say that light intensity modulation, and we are detecting at the detector, that is nothing but a conversion of that light into the electrical signal. So that's why a light detection. Similarly, we can say that here across that we'll get that a output. That output is it totally depend upon that what will be the light propagating through it. Now come to the part that is about a coherent detection. So we need to consider that whether what local oscillator we are using, so that we are detecting that particular signal at the receiver here. So that's why your output that will be proportional to the intensity here at the detector there. So now for the detection, we say that a coherence of what we can say that a coherent detection word we have used here, because we can consider that a signal frequency supposed to be transmitting at this input side is supposed to be omega 1 here, and here the detection we are detecting the signal that is supposed to be, we say that, sorry, the signal is supposed to be IF signal, and that IF signal is nothing but what, a omega 1 minus omega 2. Here we use a local oscillator of omega t frequency. So that's why we'll get that IF signal of omega 1 minus omega 2. So now we can say that a signal is mixed because of that a local oscillator here at the end. So we can consider that what will be the current detection at the detector, and the detector current is nothing but what, a coherent current, or we can say that at a detector we have the signal frequency as well as the, we can say that, a local oscillator. Signal as well as we can say that a local oscillator here. So that's why a intensity for the coherence that will be detected is depending upon that the signal frequency as well as, or we can say that, or a local oscillator signal here. Because we can say that here we are expecting that a coherent detection, so mixing takes place from this local oscillator and a signal frequency. That's why coherent current in the form of what, we can say that in the form of a signal frequency as well as the local oscillator. So if you write that ELO here, so ALO here, omega LO, okay, likewise. So we have this phase constant, that is about a pi LO. So we'll get that a current 1 by 2 A square 1 by 2 amplitude of local oscillator square AS ALO cos of omega S minus omega LO of t here into cos of theta by t. That theta is nothing but, that is about it. Here we have a plus pi t, pi of t plus theta t. Okay, this one, this. Okay, cos of omega t plus pi of t in cos of theta t. And this pi of t is equal to what? Pi of s, that is about a signal, minus your local oscillator. That's the phase difference here. And then a cos of theta of t is equal to, that is, we have a signal and local oscillator signal mod of ES, mod of EL here. Similarly, we can find out what will be the optical power at the detector we are receiving. That is proportional to what? What will be the signal power and what will be the local oscillator power. Plus twice of under root PS PL here into cos of omega S minus omega LO t plus phi of t plus cos of theta t. Okay, so that is about your, not plus into this one. Okay, so this one here it is not plus, it is into this one. Okay, cos of theta t. So even I get this one is plus here phi of t. This is into it cos into multiplication this particular bracket here. So means here we can say that omega s minus omega LO, that is nothing but what, a intermediate frequency signal of omega f. This one we say that a intermediate frequency signal. This is about local oscillator omega 1 here, omega 1 minus omega 2. So that phi of t is nothing but what, a phase difference between that a signal and a local oscillator. This one, that is about a phi of t there. And here we can say that a omega if here, it is about a difference between that signal frequency and a, we can say that a local oscillator frequency. Now, in the case of homodyne detection, we can say that heterodyne detection and a homodyne detection. In the case of a homodyne detection, what happen here? Signal carrier frequency and a local carrier frequency is same. So in the case of homodyne detection, that WIF is equal to 0. Means only if in this particular equation, if you see that P of t is equal to what? PS PLO plus twice of under root PS into PLO into cos of phi of t here, sorry, into cos of theta of t. So that is about, we can say that a homodyne detection here. Means we can say that we can use in this Coherent detection because there is a variation in the signal level there. We can say that we can use that only the variation in the amplitude or variation in the phase there. Okay, means frequency there is a no FSK component. So we can use either ASK or FSK for this homodyne detection. So since this particular case here, so we have the limitations regarding the frequency here. So that's why this is homodyne detection that can be used only for the a narrow spectral bit. Next about a heterodetection, heterodyne detection. So in this case of heterodyne detection, WIF is not equal to 0. That is about the IF frequency is not equal to 0. And then we can say that we doesn't require that optical phase loop for this detection technique. So means if we see that we can use for this because WIF is not equal to 0, so we can use a amplitude shift keying, we can use a frequency shift keying, we can use a phase shift keying. Okay, so these are about the a heterodyne detection. Now these are about the detection technique. Now we need to compare for this a receiver. So what will be the PR required? So for this a coherent detection, so we need to see the performance of the receiver. That performance of a receiver, it is in terms of a bit error rate or performance of your optical communication system. It is depending upon that what will be the bit error rate. Because we can say that a bit error rate is depends on the signal to noise ratio, and again it is depending upon that probability density function. Signal to noise ratio means what? We need to say, we need to talk about that what will be the signal level and what are the various noise in this signal to noise ratio. And then we talk about that probability density function. We talk about that what will be the probability of error when we can say that we transmit 0 but we receive the 1 output. What will be the probability of 1 and we receive that 0 there. So that is about a probability. So means we are expecting the output high or low. So according to that, we can talk about that the probability density function at the receiver there. Generally, if you consider that to talk about that receiver performance, we supposed to be consider that a BR, and then we need to talk about that for a BR, what will be the receiver sensitivity? Because signal to noise ratio, that is about we are just expecting that a level we are measuring. So we need to talk about that here. What will be the receiver sensitivity for detecting the signal there? Receiver sensitivity for detecting that homodyne detection or a heterodyne detection. Okay, that is about the different part. So we need to see that for the given optical communication system, what will be the receiver sensitivity for detecting the signal there. So that's why we need to describe that receiver sensitivity for detecting the signal in terms of that how many number of photons required to achieve the what will be the BR. So BR we can say that we are expecting the BR is to be 10 to the power minus 9. So for this 10 to the power 9 minus 9 of a BR, so how many number of photons required? So photons required means what? For the given particular light, means that is about a photon. So it will generate that electron and hole pair. And then because of generation of electron and hole pair, current is propagating through the system. And then we obtain that what will be the power received. Okay, that is nothing but a BR requirement for the receiver there. So that's why we say that what will be the quantum efficiency of a detector. Quantum efficiency, it is generally defined in terms of a average number of photons, and that will required for the generation of the electrons and hole pair. So now average number of photons per bit required, so that we say that a electron hole pair generation takes place and current is propagating through this. So now for achieving that 10 to the power minus 9, so how much will be the number of photons required per bit? Okay, means for one bit information, so how many number of photons are required for detecting the signal? So now we can talk about that. If supposed to be we have that amplitude shift keying or a on off keying technique, so in that case, what will be the average number of photons per bit required for the unity quantum efficiency? That is equal to what? 1 by 2 n plus 1 by 2 of a. So now here you can say that if photons required per bit, that is about ANP, and that is average number of photon required per bit is a half the number required for one pulse. Okay, we can say that. That's why we can say that a n dash, and we can say a zero, and that will be creating the electron hole pair. This n dash and a zero is nothing but the electron hole pairs are created for the pulse 1 and a pulse 0 there. So here that's why we can say that n is pulse 1 and this is about a pulse 0. or we can say that n dash is equal to what? A twice of np here. So if you compare that in terms of a receiving power and all, what will be the number of photons required from this equation here if we are using that OK or a ASK here? So then we need to talk about that what will be the errors here. So that's why we write here the equation of 1 by 2, that is about the power received, for the average number of a what will be the photon generated. So from this equation, if you find out so NP here, so we can say that the average number of 10 photons per bit that will be required to get a 10 to the power minus 9 BER. These are the bit required to get that 10 to the power minus 9 of a BR. So means we can say that for a given particular system, what will be the quantum limit? Quantum limit means what? A minimum number of photons required for the detection of the bit here. So that is nothing but a quantum limit. So generally we say that for the detector, if there is a one bit, then there may be, we can say that, a noise that can be a short noise, or we can say that a thermal noise. But in the case of a zero bit, it has only a thermal noise. So that's why for a given particular condition of the noise, so what will be the signal to noise ratio? What will be the signal to noise ratio so that we get that a 10 to the power minus 9 of a ABR there. So we say here what will be the minimum power required, and that minimum power required, that is nothing but a quantum limit for the detector there. So similarly we can find out what will be the minimum power requirement for the a PSK, similarly for the FSK there. Similarly we can find out the minimum power required, that is for the homodyne detection as well as the heterodyne detection. Okay, in the both the cases. So now if supposed to be, we say that here right now we are saying that detection of, we are using that ASK or OK here. So similarly we can find out what will be the minimum power required for the detection there, and then what will be the PR for the given particular equation. So we write here one directly table, and that table reflecting that a error probability of error in the case of a heterodyne and a homodyne here, and that probability of error as a function of received photons per bit for the coherent optical system. So we supposed to say that what modulation we are using, that is about a modulation. Then we supposed to say that if it is a homodyne there, what will happen? Then we can say that a heterodyne, in that case we use a synchronous detection, then we use a asynchronous detection, then we can say that a direct detection. Okay, now what will be the for the modulation okay here, amplitude shift keying or a on off keying, what will be the BR required? Okay, this is just like we say that equation of BR. BR is equal to what? EIRFC, that is the error function, and this one, how many number of bit we require, and what will be the requirement of the a quantum limit there. So that we are saying. So means we say that for a given particular this NP, okay, right now what we are saying, that is NP is nothing but a average number of a photons we require. Okay, average number of received photon required per a bit, that is about the NP we say. And then for the given particular input values, so what will be the average number of photons we require? Okay, that is, and this is about a quantum limit. Okay, so that is about for a given particular signal in the homodyne detection, suppose. So this one BR is the expression of the BR here, and then from that expression of BR we can say that how much number of photons we require. Similarly, for the synchronous detection, we can say that ERFC 1 by 2 eta NP raised to 1 by 2. Here 1 by 2 exponential of minus 1 by 2 eta NP average. Okay, average here. I just forgot here. That is about NP here. So in that case, 1 by 2 exponential of minus twice eta NP. Okay, this one is about a NP here. Means, sorry, exponential of minus 2 eta NP. Likewise. So if it is a okay on off keying, so if we can use a phase shift keying, so homodyne support only OK and a PSK here, because there is a WIF is equal to 0. Okay, so that's why it's supporting only the amplitude shift keying and a phase shift. So that's why 1 by 2 ERFC twice of eta average NP average raised to 1 by 2. Then here 1 by 2 ERFC average of NP raised to 1 by 2. And here 1 by 2 exponential of minus eta NP. Okay, that is about a PSK. Now in the frequency shift key, FSK, it's not support homodyne here. It support only the heterodyne. So it's not support a direct detection. So that equation is about 1 by 2 ERFC 1 by 2 eta NP average is to 1 by 2. And this one 1 by 2 exponential of minus 1 by 2 eta NP. This one is about a case for the FSK. Then we need to talk about that a number of photons required. Okay, we say that a number of photons required for getting the 10 to the power minus 9 DER by this ideal receiver. Okay, that's about the condition. Then again we talk about that what will be the modulation scheme here. Then we can say that a number of photon it is about homodyne. Then we can say that synchronous detection, asynchronous detection, and then the direct detection. Okay. So now we can say that on off keying. So if it is a homodyne, so we require 18 photon number of photons required to generate that 10 to the power minus 9. Here for the synchronous detection 36, 40, this one is about 10. Then if we shift key, that is about 9, 18, 20, no direct detection. If it is FSK here, no homodyne, it requires a 36. This is about a part of these three, sorry, it's two only synchronous. It is part of a heterodyne. Okay, 36, and then this one is about 40. So now if you see this table, from this table, what we it's saying, so table itself saying that a number of photons required per bit for a 10 to the power minus 9 BR. Okay, 10 to the power minus 9 BR there. So here in the case of homodyne or heterodyne there, so this table itself saying that what will be the number of photons per bit for the heterodyne or a homodyne detections it is required there. So now if you see here on off keying as well as that PS key here. So now if you consider that the number of photons required as compared to the this is three here modulation technique. So PSK, if you see that in a PSK, so it requires a low number of a photons here. Okay, less number of photons. So that's why we can say that a PSK has a better sensitivity as compared to this OK and a FSK there. And then again we say that because it requires a less number of a photons, so means that will support a narrow width. Okay, that will support the narrow width of the source there. Okay, means you can say that a PSK higher sensitivity. Okay, that is about a PSK. We can say that it's higher sensitivity, and then it has a higher sensitivity even if that sources have the very narrow line width. Okay, that is about the line width, or we can say that a narrow sources in terms of a wavelength. We can say that a line width there. So if you consider that a line width and all other factors for this PS can okay here. Suppose if you consider that a line width graph and required number of photons here, and this one is about a line width. So it is about 10 to the power minus 2, suppose 10 to the power minus 1, and this is about 1. So PSK supports a likewise a line width. So this is about a IF line width, and this one is about a line width for the PSK. And if you consider that this one is about a 0, 20, 40, 60, 80, and if you consider that OK and this is about a OK, and this one is about a FSK here, and this one is about 10, 20, 50. That is about a gigabits per second, or we can say that in terms of a megahertz, 10 megahertz, 20, that is about gigabits per megahertz there. Okay, so 10, 20, 100 likewise. Okay, so that's why we can say that a PSK supports for this low bit there. So that's all about a coherent detection and a optical reserve performance. What will be the minimum number of photons required for the detection of the signal? So that we shall stop here.